Okay, now the next topic that we have to consider is again the Fourier series coefficients, but this time the Fourier series coefficients or the Fourier series representation of discrete time periodic signals. This is the new topic. As you see, periodicity is an important issue here. We must have a periodic signal in order to find the Fourier series representation. The first example that we started, or the first part of this chapter, was dedicated to continuous time periodic signals, and we found the methodology to find the Fourier series coefficients of continuous time periodic signals. This time it's Fourier series representations of discrete time periodic signals. Now, what is a periodic signal in discrete time? It must have this property. X of n must be equal to x of n plus capital N for some capital N an element of integers. Alright? So the period, the trick here is the period for a discrete time periodic signal must be an integer. Okay? And then we have, from this period, we construct a so-called fundamental frequency. Of course, this capital N can also be considered as the fundamental period. If you combine two discrete time periodic signals, one with a period of 5 and the other one with a period of 7, for example, what would be the period, the fundamental period? The least common multiple, again, of 5 and 7 will be 35. So the fundamental period will be 35. That would be capital N. And from there, we must find the fundamental frequency to be equal to 2 pi over the fundamental period. And then we can represent our signal. The theory, the Fourier series theory, states that we can represent our periodic signal x of n as a combination of Fourier series coefficients, again, times the harmonics. And the harmonics must be k times omega 0, an integer times the fundamental frequency, times n. Or, you see that this expression is the same as the time, as the continuous time Fourier series representation. Up to now, they look the same. ak e to the j k times 2 pi over capital N times n. If you wish, you can write it like this too. The problem or the difference between the continuous time Fourier series representation and the discrete time Fourier series representation is the fact that this k index along this summation is not infinity for this case. For the continuous Fourier series representation, this k starts from minus infinity and goes up to plus infinity for all k's. But now, since it's in the form of 2 pi over an integer, a deliberately integer n, look what happens. So, k from where to where is the question. How many Fourier series coefficients do we have? We are trying to answer that question right now. Now, let's think of k is equal to some number, let's say 1, and then we have e to the j times 2 pi over capital N times n. Okay, let's say that it is 1. Or it may be an easier idea to think of k is equal to 0. Let's start from here, an easier example. K is equal to 0, then it is equal to e to the j 0 times 2 pi over n, which is e to the 0, which is 1. Okay? This complex exponential will give you 1. How about k is equal to 0 plus capital N? What if we proceed on the running from zero, from minus infinity to infinity, somewhere in between we have k is equal to 0. Now let's go a little bit further and see what's happening at k is equal to n. If k is equal to n, then it will be e to the j n times 2 pi over n times n. And these n's will cancel. It will be e to the j 2 pi n. What is that? It's again 1. So this gives you a hint about the circular behavior of this e to the j 2 pi over capital N times k thing. If you increase the k by capital N, you come to the same point. You circle around and come to the same point. In fact, if k is equal to 1, it would be e to the j 2 pi over capital N n. And if k is equal to n plus 1, then it would be e to the j n plus 1 2 pi over n n. And when you expand it, it will be e to the j n times 2 pi over n n times e to the j 1 2 pi over n n. And you see that this portion is 1. So the remaining thing is the same as k is equal to 1 case. So if you are at k is equal to 1, capital N plus 1 will give you the same harmonic. If k is equal to 2, 2 plus capital N will correspond to the same harmonic. So the number of harmonics are limited here. They are repeating themselves always. And we have to limit our summation of ak e to the j k 2 pi over n n thing in a summation running index from, let's say, k is equal to 0 to n minus 1. Because when k reaches to n, 1 after n minus 1 will be n. That would be the same as k is equal to 0 case. And they are constantly repeating themselves. So you must limit your summation to a duration of capital N. Which means there are only capital N distinct harmonics. Unlike infinite number of harmonics for the continuous case. For the continuous case, this doesn't happen. I mean, we do not correspond to the same harmonic after so many Fourier series coefficient indices. For all k from minus infinity to infinity, we may have a case, infinitely many a case. But for discrete time, if the period is capital N, then it means you have only capital N harmonics. And then these harmonics are repeating themselves, you have to conclude. For example, if you have found a 0, and the signal is periodic with 8, period 8, discrete time. What can you say about A8? A8 is the same as A0. They are periodically repeating themselves. The harmonics are repeating themselves. A1 is the same as A9. A2 is the same as A10. So let's write it. If n is equal to 8, then A0 is the same as A8. A minus 1 is the same as A7. A2 is the same as A10. So AK is equal to AK plus some integer times capital N. That integer can be 1, 2, or 0, whatever. So the Fourier series coefficients are also periodically repeating. And in order to solve accurately a question, when I say find the Fourier series coefficients, what you have to do is you have to give me capital N Fourier series coefficients only, not more than that, because then they are repeating themselves. Of course, those Fourier series coefficients can be from 0 to n minus 1, or it can be from minus n over 2 to plus n over 2, some intermediate range as well. For example, if it is, again, periodic by 8, then you can give me A0, A1, A2, A3, A4, A5, A6, A7 as one answer, or you can give me A minus 2, A minus 1, A0, A1, A2, A3, A4, and A5 as well. It doesn't matter which you are giving me, because anyway, as you see, this A minus 2 is the same as A6. This one here is the same as A6 here. It's 8 periodic anyway, so you can tell me like that. Of course, I will give you the formula for extracting or evaluating the Fourier series coefficients, just like the formula for the Fourier series coefficients in the continuous time domain. And in that formula, we will have a summation, and that summation can be easily evaluated if you start from some place and end at some other place, and it will give you some certain index, A minus 2, A minus 1, or whatever. So you have to make your guesses right to give me either this one, or 6 other possibilities. As a matter of fact, we can give it in 8 different ways. Alright, now what is the formula for that? The extraction of the formula for Fourier series coefficient in discrete time periodic signals is a little bit cumbersome. If you remember how we found the formula for this continuous time AK, we took integrals of both sides of the equation and then cancelled some other terms and then say that AK is therefore the rest. The extraction or the motivation behind finding the formula for AK is similar here, and it's in the book, and it is only for the curious. Okay, I don't want to go into the details of that. You will probably not remember that, and it will not help you solve any questions. It may help you to better understand what that AK is and how we can extract those things if you want to improve your skills. But in general, the formulas that you need to remember are the final formulas for the Fourier series representation in discrete time, and they are this. First of all, the Fourier series representation I'm repeating, but this time I'm repeating with a different notation, K in a duration of capital N. Now this new representation is telling you that it can be from 0 to n minus 1, it can be from 1 to n, or 2 to n plus 1, or minus 1 to n minus 2. Okay, so the duration is capital N, it says. Depending on where you start, you must end at the appropriate place. AK e to the j k 2 pi over capital N n. So this is the Fourier series representation, and the formula to find AK is 1 over n, where n is of course the fundamental period, summation, again in a duration of capital N. Wherever you start, you must end n points later. The summation x of n times e to the minus j k 2 pi over n n. Now you see the two formulas, the top one and the bottom one, are very similar to each other, and that is that's the property of Fourier. Okay. In the representation itself, for the time domain, the top one, you have positive exponents e to the j k omega 0 n. For the representation of the frequency domain, AK, for example, it is e to the minus jk 2 pi over n. And this 1 over n, previously in the integral formula for the Fourier series representation in time domain, there was a 1 over 2 pi and there was an integration. But apart from that, the exponentials are conjugates of each other. They are always like this. Okay? You can remember without looking at the formulas like this. The time domain representation has positive exponents. The frequency domain representations have negative exponents, e to the minus j k omega 0 n. Okay, that's quite an easy way to remember these things. And these two formulas will mean the discrete time Fourier series representation. Now let's see an example, and this example is so trivial that it doesn't require, again, these formulas to apply. And the only case that doesn't require these formulas are the cosines and sines. The cosines and sines are simple periodic functions which don't require any evaluation of these formulas, AKs. Just use the Euler's expansion and then you are done. Okay? And the example is like that. X of n is equal to sine 2 pi over capital N, and for some certain n, let's say n is equal to, I don't know, 5, whatever. Okay? So this is a periodic signal because capital N corresponds to an integer. And the period is 5. And capital N is the period, as you see. And the way to find the Fourier series representation is like this: 1 over 2j e to the j 2 pi over capital N minus 1 over 2j e to the minus j 2 pi over capital N. This is the Euler's expansion, which says that there are two harmonics in this signal, and the values or the coefficients of these harmonics are 1 over 2j and minus 1 over 2j. And since there is no other harmonic, they do correspond to the fundamental harmonic as well. So A1 is 2 pi over capital N times 1 here, and then this is the Fourier series coefficient. A1 is equal to 1 over 2j, and the other one is A minus 1. At k is equal to minus 1, we have minus 2 pi over capital N as the frequency, and the value here is minus 1 over 2j. The two Fourier series coefficients are evaluated simply like this. In order to be more complete, more mathematically complete, you can say that A1 plus some integer times the period is also equal to 1 over 2j, and A minus 1 plus some integer times the period is also equal to minus 1 over 2j, because they are repeating themselves. Which means if n is equal to 5, for example, then A1 is equal to 1 over 2j, and A6 is also 1 over 2j. A11 is equal to 1 over 2j. A16 is equal to 1 over 2j. And A minus 1 is equal to minus 1 over 2j, which means what is the next positive index? A4. Minus 1 plus 5 is 4. So A4 is also equal to minus 1 over 2j. If you try to plot these things, by the way, these are complex values, so you cannot normally plot complex values, but let's assume that 1 over j is something that can be drawn. It is like this: you have a 0 point, and at 1 you have 1 over 2j. Let's assume it's like positive, and the other one is at, so this is 0, this is 1, this is minus 1. At minus 1 it is minus 1 over 2j. 2, 3, 4, 5. So 5 is like 0, and then all the pattern repeats itself, which says that at 1 before 5, which is 4, you have this, and 1 after 5, which is at 6, you have this. So these two positive and negative things are repeating themselves at periods of 5. 6, 7, 8, 9, 10. So at 9 it is negative, at 11 it is positive. And same is valid for minus 2, minus 3, minus 4, minus 5, minus 6. Sorry. Minus 1, minus 2, minus 3, minus 4. Yes, it is here. Minus 5. And like this. It's also repeating towards the left hand side and towards the right hand side. And this is an index for k, let's say. And these are the plots of AKs on the k-axis. But of course, as you see, these are trivial examples, as your friend have nicely indicated. We are seeing some normal, easy, trivial examples, and suddenly on the examination we come up with a question which is not like the examples that we see, but the case for the examination is similar to this one. Let's have another quick example. X of n is equal to sine 2 pi over 5n plus cosine 2 pi over 6n. Okay, it really resembles the exam question now. What are the Fourier series coefficients? Again, the trick here is to determine the fundamental period and the fundamental frequency. And with respect to the fundamental frequency, which index does this correspond to? The first one, does the first one correspond to? And which index does the second one correspond to? What is k for this? First of all, what is the fundamental period? The fundamental period is least common multiple of 5 and 6, which is 30, just like the exam. Therefore, the fundamental frequency is 2 pi over 30. Now, if we want to represent x of n using the Euler's expansion, what will it be? It will be 1 over 2j e to the j 2 pi over 5n minus 1 over 2j e to the j 2 pi over 5n minus j 2 pi over 5n and plus 1 over 2 e to the j 2 pi over 6n plus 1 over 2 e to the minus j 2 pi over 6n. Are we settled here? I just expanded the sine and the cosine in Euler's expansion in two terms, like this. However, as you see, there are four Fourier series coefficients available here. This will have a Fourier series coefficient of k, let's say, and this will have a Fourier series coefficient of minus k. Minus k, and then this will correspond to a Fourier series coefficient of L, and this will correspond to a Fourier series coefficient of minus L, because they are inverses of each other. Now, what is k? Let's start from that. K is such that e to the j 2 pi over 5n is equal to e to the j k times omega 0 n. Omega 0 is 2 pi over 30 n. So what is k? 6. And therefore this is the sixth harmonic, and this is the sixth Fourier series coefficient. What does this correspond to? What is the coefficient of that? Minus 6, the reciprocal of that. Now let's think of the other one. E to the j 2 pi over 6n is equal to e to the j l times 2 pi over 30 n. Now, then what is L? Huh? 5. It's the same question, as a matter of fact. And this is the fifth Fourier series coefficient there for this 1 over 2. And the other 1 over 2 is L is equal to minus 5 case, minus fifth. So you can give the answer like this. You say that A5 is equal to A minus 5 is equal to 1 over 2. A6 is equal to 1 over 2j. A minus 6 is equal to minus 1 over 2j. Okay? So these are the Fourier series coefficients. Suppose that I push a little bit further to ask you to give me the harmonics or the Fourier series coefficients between 0 and the periods, 0 and 30. So I don't want you to tell me what A minus 5 is. I want you to give me the values between A0 and A29. Because the period is 30. So what are they? A5 and A6 are there, no problem. But we must have 2 more harmonics corresponding to 2 more Fourier series coefficients. What are their indices? First of all, A minus 5 is equal to A n minus 5, or A minus 5 plus n, which is A 30 minus 5, which is A 25. And that is equal to 1 over 2. So A5 is 1 over 2 and A25 is 1 over 2. Or you can say A minus 5. They are the same. Okay? That's what I'm trying to emphasize here. And A minus 6 is equal to A n minus 6, which is A 30 minus 6, which is A 24 is equal to minus 1 over 2j. So the harmonics are A5, A6, A24 and A25. 4 harmonics. And then they repeat themselves. How do they repeat? It's like A5 is somewhere here and A6 is somewhere here, because as you see it is complex, so I'm trying to represent it somehow. And then this is 5, this is 6, 7, 8, 9, 10, 11, 12, 13, 14, 18, 19, 20, 21, 22, 23, 24. Yeah, I arrived at 24. It's like this. 24 is this. It's the negative of the complex thing, so perhaps I should draw it like this: minus 1 over 2j. And then at A25, I have a plus 1 over 2. So this one and this one are the same. This one is the conjugate of this one. This is 1 over 2j, this is minus 1 over 2j. And they happen to be at minus 5 and at minus 6 as well. And they are repeating. Of course, if I could have a longer axis, at the right hand side of the rightmost thing, I should be able to draw a repetition of these again. Where are they? They will be at 25 and 26. Oh, sorry, 35 and 36. Far away to the right. So these are the Fourier series coefficients for using the Euler's expansion, and as you see, the critical step is to determine the fundamental period. And with respect to the fundamental period and hence the fundamental frequency, how many times with an integer do I need to multiply to get to the frequency here and the frequency here? They will be A6 and A5 for these examples. If you have 3 components, then you have to find the least common multiple of those 3. Okay, so this much is an example for the Euler's expansion. Starting tomorrow, we will start seeing examples of this formula. we will need to use this formula. So let's stop at this point.